the notes for AP Calculus on the topic of the shell method continued. So this first one we'll do without a calculator, and the second one we'll do with the calculator. So this says let R be the region in the first quadrant bounded by the graphs. So that's the boundary of them. Y equals x squared, y equals 0, and x equals 2. Okay, so let's sketch those first. Let's start with the easy ones. X equals 2, where the x coordinate is always 2. That creates a vertical line. X is 2 right here. That's one of our boundaries. Then we've also got y equals 0, creates a horizontal line. Where y is 0 is right on the x-axis here. Now let's go ahead and label these two. So here's x equals 2. There's y equals 0. And then we've got our parabola here. So sometimes without a calculator you can set them equal to each other. You can set the ones that are y equal to each other, so x squared equals 0. You can see that would just give you 0 as the point of intersection. But other times you can just substitute in points to see what it looks like here when it's simple here, and we want to know what it is when x equals 2. So if we plug in 2, 2 squared is 4. So 2 is up here at 4. And then you get one more point since it's a parabola, and it has to have at least 3 points since it's a curve. If you substitute in 1, 1 squared is 1. So you can see we get this parabola like that. So there's y equals x squared. So you see the region of the first quadrant bounded by all three of them is right in here. So let's go ahead and draw a representative rectangle there. And then that's the infinitely small change in x there, dx. And then it says find the volume of the solid generated when the region R, so this region is revolved about the line x equals 1. Sorry, x equals 3. So x equals 3, let's draw that one as a dotted line, since it is not enclosing anything, it's just our axis of revolution. Over here at x equals 3. Okay, so we're taking this region here, it's coming out of the board and revolving around this axis. You can indicate that with like a circular arrow there. And so this is called the shell method because if you look at this one representative rectangle, when you revolve that around this axis of revolution, you can see it forms what's called a cylindrical shell. Think of it kind of like the shape of like a paper towel roll made out of cardboard there. So what we have here is a whole bunch of these different size cylindrical shells, one inside the other. And it's helpful to kind of figure out the two components of this. You don't have to do this, but to see that, what I'd recommend is draw a representative cylindrical shell so you can easily see what the radius and the height is. You can just try to wrap it around this axis of revolution as best you can. So that would be our one representative cylindrical shell there. And that way you can see the radius and height more easily of that cylindrical shell. So the two components we want to figure out are p of x and h of x. So the height on these, you can see the height of the cylinder is just the same as the length of the rectangle. So there's h of x. So let's figure out what h of x would equal. Well, any vertical distance you're figuring out, you take the one on the top minus the one on the bottom, because the one on top has a larger y coordinate. So the one on top here of h of x would be x squared, minus the one on the bottom, you can see is just y equals 0, so minus 0. So just ends up being x squared. Notice this h of x, this is what you would integrate if you were just finding an area. It would be just this integral from 0 to 2. But we also need the radius, and on these, we usually refer to the radius as p of x. So the radius, you can see, goes from the axis of revolution to a rectangle. So you can apply a similar principle to see what the radius would be. Remember, for the h of x, we did the top minus the bottom. When you have a horizontal distance, you have one on the right and one on the left, and you always start with the one on the right, because that has the larger x coordinate. Just like we do top minus the bottom, because the one on the top has a larger y coordinate. So in this case, the one on the right, notice, is our axis of revolution, so it'd be 3. Minus, when you're doing a horizontal distance here, the rectangle always represents where an x coordinate is, wherever you drew this rectangle. So it'd be 3 minus x would be our radius p of x of the cylindrical shell. Another way to see why the 3 minus x makes sense is if you look here, you can see this whole distance back to the y-axis here, that's 3. And this distance right here to the rectangle, that's the x coordinate, this function. So you can see if you did 3 minus x, that would give you the correct p of x radius. And this we're going to set up without a calculator. So remember, the formula comes from the surface area of a cylinder. So which is 2 pi r h. And so we have the 2 pi as the constant on the outside. Then the integral, everything's in terms of x here. It starts at x equals 0 right here and stops at x equals 2 because of the vertical line. So it'd be from 0 to 2. And then we multiply p of x times h of x. So it'd be p of x, which is 3 minus x, times h of x, which is x squared. And then you might think, well, this is surface area formula. How's it going to give us volume? Well, what turns it into volume is multiplying by the thickness, which is dx. And then what we're doing by integrating, we're integrating all of these cylindrical shells, starting from 0, the ones right here, all the way till 2. And notice with the shell method, unlike the disk method, you don't have to worry about whether or not there's a hole, because in this case you can see there is this hole right in here when you revolve it around. These cylindrical shells are automatically hollow in the inside, so they automatically always account for any holes anyway. So there's no need to worry about those, unlike the disk method when you're setting it up here. And another thing to help you keep from getting the disk method and shell method mixed up, remember with the disk method, we saw if the rectangle and axis of revolution were perpendicular, it would be the disk method. Here you can see, here's our rectangle. Just drawing it up the side here. Dx, and here's our axis of revolution. You can say they're not perpendicular, here they're parallel, parashell. Right. So that's just a mnemonic device to make it easy to remember which method you'll be using, since they both look very similar in the wording. They're both revolved around an axis, but that's how you can tell whether it's going to be the disk method or the shell method. All right, so now we just have to make this easier to integrate, because remember there's no product rule for integration, and there's no need to use integration by parts here. So we'll have 2 pi on the outside. Then if we just distribute this x squared out to make it easier to integrate, integral from 0 to 2, then we'll have 3x squared minus x cubed times dx. And now we can integrate it. So we integrate 3x squared, we get 3x cubed over 3 minus x to the 4th over 4. From 0 to 2, and we still have the 2 pi out in front. And then you can see we can reduce that a little bit. The 3's reduced out here. So we just end up with x cubed minus x to the 4th over 4. So now we always start with the upper limit. So when we substitute that in, substitute in the 2 cubed gives you 8. Minus 2 squared is 16 divided by 4 is 4. And then minus, when you substitute in 0, notice they're both going to be 0. So 8 minus 4 would just give you 4 times 2 pi would give you 8 pi. Now sometimes you're going to end up with fractional answers. In this case it just happens not to be a fractional answer. You can leave your answer in terms of pi. And then if you want to, you can put units cubed to remind yourself it represents the volume of this three-dimensional shape. But since you aren't given specific units, you don't have to. All right, let's take a look at one more, but this time we'll look at with the graphing calculator on this one. Okay, so this one says let R be the region enclosed by the graphs of, and I apologize, I didn't realize until I'd already typed this up here. There's a typo on here because it will create a vertical asymptote in a region. So instead of -4, cross out the 4 there and change it to -30. And then g of x is 1/10 x to the 4th minus 3. So once we change it to that, let's go ahead and enter these into our calculator. You can see this would be difficult to solve without a calculator because if you try to set them equal to each other, it's going to be tough to solve with a natural log equal to this function right here. So let's go ahead and look at both calculators. So let's start with the 84 here. I'll clear these out so you can see it entering in here. And f of x, we've got x cubed, natural log of x cubed minus 30. So first natural log right here. Whoops, let's go to y1 for that one. Natural log, and then to get the absolute value, remember on the TI-83 or 84, you first hit math, and then hit the right arrow, go over to num for number, and then it's the very first one, ABS. It stands for absolute value. And then we've got x cubed. So x, here's the exponent caret button cubed, and then minus 30. And then we just got to be careful with our parentheses. We need a close parentheses on the absolute value, and then another close parentheses on the logarithm. And then for y2, we've got 1/10 out in front, so one way to do it, you could put in parentheses 1/10. And then x to the 4th, or you could write it as 0.1 if you prefer. As a decimal, that would work also. X to the 4th, and then minus 3. And let's change our window size here. So window, and then to make it fit on here, I just change it to -5 to 5 on the x minimax, and the y minimax -4 to 4, just so we can kind of zoom in on this region. And you can play around with it until you can see the region close. And then it's going to graph them, remember, in the order we typed them in. So when you hit graph, there's the graph of the natural log of x cubed minus 30, and there's the graph of g of x, 1/10 x to the 4th minus 3. So notice it's hard to see here. It looks like it's a cusp, but actually what's happening, there's actually a vertical asymptote right here, because what's happening right at this point is the natural log, the x coordinate, right here would be the cube root of 30. Cubed is 30, 30 minus 30 is 0. So even though the absolute value sign's there, you still can't have the natural log of 0. That's what's happening right at this point on the graph here. Previously, when I had the 4 there, it had a vertical asymptote right in our region. So, and I didn't realize that's what it was until I looked at it more carefully, and that's why I had to change it to minus 30. So that vertical asymptote would no longer be in our region enclosed. All right, so let's go ahead and sketch what these look like here. So let's sketch f of x here. For the part that's relevant to us, sorry about that, it goes something like this. And then for g of x, let's see, it kind of looks like a wide parabola in a way. Shifted down 3. So it looks something like this. Just so you can see that region enclosed. And we draw a representative rectangle somewhere in there. Alright, so we're going to revolve it this time about the line x equals -4, so let's draw that as a dotted line, so it doesn't confuse us as to what the region enclosed is. so there's x equals -4. And that's what we're revolving this region around. So a little circular arrow. And again, you can see the axis revolution and the rectangle are parallel, so parashell, so it's the shell method. This one, I didn't quite leave myself enough room, you might have a little more room on yours, to draw a representative cylindrical shell. But it would basically look like this. Wrapping around our axis of revolution here. You can see a little more than half of it there. And so again, we need the two components here, the height. Let's start with that one because that's usually easy to figure out. It's just always the length of our rectangle, h of x. You can see it would be the top one, which is, oops, I forgot to label these. Here's f of x right here, and this one is g of x. So h of x, the top on our rectangle, you can see is f of x, minus the one on the bottom is g of x. And then the radius, you can see would go from our axis of revolution to the rectangle. There's p of x. And this time the one on the right is x. And the one on the left here is our axis of revolution, -4. So the x minus -4, which you can see is simplified to be x plus 4. And another way to see why x plus 4 makes sense is notice this distance from here to here, that's our x coordinate. And this distance from here to the axis of revolution is 4. From the y-axis to the axis of revolution, so it would be x plus 4 as the radius of our cylindrical shell there. So let's go ahead and put these in the spire here. We'll look at both calculators, how we go about the next steps. All right, so for the Inspire, first, new document and add graphs. F1 is natural log, so it's right above the e to the x. Control natural log. Absolute value you can get right next to the number 9 right here. Here's the absolute value signs. And then x is right down at the bottom to the third. And then hit the right arrow to get out of the exponent, minus 30. I already added the closed parentheses for us on the natural log. And then tab, enter in F2 or g of x. That one is 1/10. You can do the fraction button right next to the 9 there, just like it looks on paper. So 1/10, and then x to the 4th. Hit the right arrow to get out of the exponent, minus 3. So you can see our region enclosed there. Again, to change the window size, menu, analyze graph. You don't have to change it, but, window zoom, window settings. And then you can go -5 to 5 on the X minimax if you want to zoom in on it, and negative, remember the negative out in front is with the parentheses there. -4 to 4 on the Y minimax. Zoom in on a little more. All right, now let's go ahead and figure out our points of intersection with both calculators. And you can call them whatever you want here, but I'm just going to use capital letters in the first two letters of the alphabet. So this right here, this point of intersection, x coordinate will be capital A, and where our origin stops, capital B. So we've got to write it down on our paper as well as store them in our calculator. So for A, you go second calc, 84 intersect number 5. First curve, y1, just hit enter. Second curve, y2, hit enter. And then guess, you can move the cursor over there, or I'm going to guess it's about -3. And there's the x coordinate there, negative 2.891 rounds to 2, right, to at least the thousandths place accuracy. And let's store it in our calculator. So second quit, store alpha A, enter. And then let's find the other one, second calc, intersect. Number 5, first curve, enter for y1, second curve, y2, enter. And then guess, this time I'll guess it's over at, I don't want to go to past the vertical asymptote here, so I'm going to guess 2.5 to be on the safe side. And it's 2.7019 rounds to 2.702. You can write the whole thing or at least to the thousandths place. And then quit out of there. So second quit and store alpha B. Enter. And now let's look at how we do the same thing on the Inspire. So Inspire, you go menu, analyze graph, intersection, lower bound. Let's find this one, just make the vertical line here to the left of the point intersection, upper bound to the right of it. And then it gives it to you, highlight the x coordinate, which is what we want, hit the var button, and then number 1 store, and then type in A, enter, and now it's in bold, that's A. And let's find the other one, the same process, menu, analyze graph, intersection, lower bound, click a little bit to the left of it, upper bound a little to the right of it. There it is, highlight it, var, store variable, and then type in B and enter. And now let's go ahead and set up our integral here now that we've found A and B. So back to paper. And again, be very careful on how you write the integral, because remember most of the points, both on AP exam as well as my exam, are going to be for setting it up correctly, the integral. So again, it's a shell method. So it comes from the formula for the surface area of the part that wraps around the cylinder. So 2 pi on the outside. Integral in this case from A to B, which we just found, our points of intersection. And then it's P of x times H of x. So P of x is x plus 4. And H of x, f of x minus g of x. This thing to be careful about here, and then times dx, is remember when you're writing down the integral, don't put y1 minus y2 here. That's only for our calculators. You lose a lot of points because nobody but you and your calculator use y1 or y2. Or the same thing if you have Inspire, don't put f1 of x minus f2 of x. The only way you could do that is if you wanted to find them up above. y1 and y2 you can't use at all because they're not functions of x. If you want to use f1 of x and f2 of x, you could, but then what you'd have to do is write down f1 of x equals f of x, and then f2 of x equals g of x. Then you could put f1 of x minus f2 of x, but to me that's more work. Why would you do that when you can just use f and g here? So it's easier to do it that way, with just the original functions we give you. Or if they're y equals, not given function names, then you could write f1 of x equals the whole thing, f2 of x equals the whole thing, and then put those in there. But again, it might be easier to just write the functions in here as they are anyway. All right, so let's see how we evaluate this with our calculator. So we've got 2 pi on the outside. Go back to the 84 here. So 2 pi, and then math, number 9. Function integrate. And then we've got x plus 4, so parentheses, x plus 4, close parentheses, and then open parentheses, f of x, that was our y1, bars, go to y variables, number 1 function, y1 minus bars, go to y variables, number 1, and then y2, close parentheses on that, and then comma, and then x, comma, lower limit alpha a, comma, upper limit alpha b. Or if you have the newer 84s, it's going to look more like the the Inspire format where you still have all the same information, you just put things exactly like, kind of like they look on paper. You put the x plus 4 at y1 minus y2 right here, you put the a and the b where they are in the integral, and you put the x here with the dx. And you can see we got 707.964 is our volume. Again, always be accurate to at least the thousandths place. And if you want, you can put units cubed, but you don't have to remind you that it's volume we're talking about here. And then for the Inspire, where you do the same thing, you go dock, insert calculator, and then we'll have 2 pi. Pi is right next to the h here. And then the integrals again are on the button right next to the 9. See the definite integral one looks like this. And then a lower limit, b upper limit. This is again kind of what the newer 84s format looks like. And then open parentheses, x plus 4. Now be careful on the Inspire. If you put just parentheses, things right next to each other on the Inspire, it doesn't always recognize that you want to multiply. It'll sometimes give you an error, especially with trig functions, like if you put x sine x, you have to put a multiplication sign right here. So just to be on the safe side with Inspire, rather than putting things just right next to each other, just put actually the times sign to ensure you won't get that error. And it doesn't happen on the 84, but on the Inspire it sometimes does. So then parentheses, open parentheses, and then we had f1 was our first one, f1 of x, and then minus bar f2x. And then our variable is x right there. And we can see we get the same answer. And that concludes the notes for AP Calculus on the topic of the shell method continued.